Subscribe our channel, press the bell icon for latest videos.
Hi friends, here in this video we are going to see the flexural equation or flexural formula. So let's get started. Now what is flexural equation or flexural formula? For that I'll just quickly draw the diagram. Here there is a beam having length capital L supported at ends A and B under the action of the load which is kept at the center, load W. Now because of this the beam is going to bend. So in case of flexural formula we are considering only the bending effect and not the shearing of the beam, or we can say the shearing stresses. Here there is a line which shows the neutral layer, or we can say the neutral axis, and it is that axis whose length remains constant even after bending of the column. So here we have this neutral axis, bending of the beam, not a column, and here since it is bending with respect to a center, there will be a radius of curvature denoted by capital R. So I'll quickly write down the flexural formula. So this is the flexural equation. Here I'll define the terms, like starting with M. So this is the flexural formula where M is called as the maximum bending moment. It would be in terms of Newton mm. I is the moment of inertia about the neutral axis. It is mm raised to 4, and the cross section may change. Here I am taking an example of a rectangular cross section. It can be I section, T section, C section, or it can be circular, hollow circular, any given section. So we have to find the moment of inertia for that section about the neutral axis. Next, sigma b is the bending stress, and if we are taking maximum bending moment and maximum value of y, that would give us the maximum bending stress, Newton per mm square. And y is the distance from neutral axis to the topmost or the bottommost fiber. So from the neutral axis to the topmost fiber, the distance is y. Similarly, from the neutral axis up to the bottommost layer or bottommost fiber, it is distance y. Then if we are taking again the maximum distance of y would give us the maximum bending stress at the top and at the bottom. And as we see here, at the center the value of y is 0, so at the center the bending stress would be 0. Then capital E is the Young's modulus for the beam material, which can depend upon the type of material we are selecting, and R is the radius of curvature of the beam, as we can see over here. So in short, this was the flexural equation. At the end, if you all find my videos helpful, you all can like, share, comment and subscribe our channel and share it amongst your family and friends. Thanks for watching.